Suppose a blood bank is in need of type A blood. 40% of people have type A blood. Before we go further, I'd just like to give you some basic information about blood donation because it's important. So, some facts. The number of whole blood and red blood cell units collected in the U.S. per year is 13.6 million. The number of blood donors in the United States in each year is 6.8 million. Fact 3. Although an estimated 38% of the U.S. population is eligible to donate blood at any given time, less than 10% of those eligible actually do donate. Fact 4. Blood cannot be manufactured. It can only come from donations. And the final fact today, type O negative blood can be transfused to patients of all blood types. It is always in great demand and often in short supply. A lot of the geometric random variables deal with blood donation problems, and so that's why I wanted to take a moment to go over that. So let's continue on with the problem. How many donations should we expect to collect until we find the first donation of type A blood? So we see this word until, and that's a clue that we're dealing with potentially a geometric distribution. What are the other components that we have to look at? Let's think bits. We have a binary situation because either a person is classified as type A blood type or not. Each individual donor we're assuming is independent. T, we're waiting until we see the first donation of type A blood. And S, it's the same probability for each individual. So we have bits, and therefore we can use the formulas for geometric distribution. The expected value formula is 1 over P. So in this case, it's 1 over 0.4, which is equal to 2.5. So we would expect to see 2.5 donors before we encounter the first person with type A blood. What's the standard deviation? The standard deviation formula for the geometric distribution is the square root of Q over P squared, where Q is equal to 1 minus P. So therefore, in this case, Q is 0.6. 1 minus 0.4 is 0.6 over 0.4 squared. And after I enter it in the calculator, I would get approximately 1.94. And that shows how much it would vary for each trial. And for the last part of this first example, they want us to complete a probability distribution function where X represents the number of people until we encounter a type A donor. And the formula, if you recall from the other video, is Q, which is actually 1 minus P, raised to the number of trials before the one we're expecting to see, times P. And I don't actually use this, but in case you wanted to have it available, it's right there. So suppose K was 1. For this case, we're expecting to see the very first donor is a type A blood person, and so therefore it would simply be 0.4. Now let's look at example 2. We're expecting one person who wasn't type A, so that would be 0.6, times the person with type A. Let me write it down here instead. That would be 0.4, and if I multiply that out, I would get 0.24. Now for the third scenario, suppose I don't see that type A person until the third donor. There would be 2 people who don't have type A blood times the person with the type A blood. And when we multiply that out, we get 0.144. And now let's do the case where K is 4. We're going to see that type A donor on the 4th trial. So that would be 3 people who were not times the type A donor. And if I multiply that out, I would get 0.0864. And you notice how the values are decreasing. And this would go on infinitely until you would actually encounter someone with type A blood. But as K increases, this whole value is going to start decreasing. Example 2. About 8% of males are colorblind. A researcher needs some colorblind subjects for an experiment and begins checking potential subjects. On average, that's a key word, how many men should the researcher expect to check to find one who's colorblind? Well, let's first see if the conditions for the geometric distribution match. Either a person is colorblind or not, so that would be B. I, each individual is independent from one another, that's the I. T, we're waiting until we see someone who's colorblind, again that keyword until. And S, it's the same chance of being colorblind for each person. So therefore we can use the formulas for geometric distribution. So to get the expected value, it would just be 1 over P. So in this case, it would be 1 over 0.08. And when we enter that into the calculator, we get 12.5. So on average, we would expect to see 12.5 subjects before we encounter someone who's colorblind. What is the probability that the first colorblind man found would be the 6th person check? Okay, until the 6th person. So again, in this case, we're expecting to see the person on the 6th subject that we encounter. So that means there are 5 people, and again, each person is independent, so we could just multiply it together, times the subject who is colorblind. And when we multiply that out, we get 0.0527. And for the last part of the problem, what is the probability that she finds someone who's colorblind before checking the 10th person? And this question's a little bit different. We're saying that that means that it could be on any trial prior to the 10th person. In other words, the researcher could have found the person on the first encounter, or maybe on the second encounter, or maybe not until the 9th encounter. And you're going to have to evaluate each of these probabilities and then add them up. So if they encounter the person on the first trial, that would be 0.08. On the second one, that means they didn't get it on the first, but they got it on the second. When x is equal to 3, that would be the first 2 people they didn't encounter, but the third they didn't. And then ... On the last encounter, if x is 9, that means there are 8 people that weren't colorblind, but that 9th person was colorblind. I'm going to show you how I'm going to enter it in the calculator, but I do have a separate video that you can watch more closely on how I do this. there is so it is geometric CDF, and the parameters that you are going to enter is the probability and then the minimum value that you're looking at and the maximum. So in this case, it's going to be geometric CDF, and the probability of being colorblind is 0.08, and the lowest value we're looking at is when X is 1, and the highest is when X is 9. And so you're going to hit Menu, Statistics, and Distributions, option number 5, and then we're going to slowly, let me put this on hold a sec. So it's Menu, Statistics, Distribution, and it's option number I. And in this case, the probability of being colorblind is 0.08, the lower bound is 1, and the upper bound is 9. And we press enter, and we can see that the answer is 0.5278. I'll be doing an additional training on the use of the calculator in a separate video, and I do hope that this helps give you some understanding of how to use geometric distributions.